Hello everyone. This video is about an analysis of a tensile data which we actually obtain after a tensile testing of a metallic material. So on the right hand side you can see a figure. This is an Instron tensile testing machine. This machine is normally used to test any metallic material under the tensile load. So this machine is available in different capacities. So the machine that we have used today for this demonstration, it is 50.2 kilonewton Instron machine. So as you can see here, whenever we manufacture any material through casting, extrusion, or different manufacturing techniques, we can machine samples for tensile testing. So we can make cylindrical samples, as you can see here, or we can make uh, rectangular samples with different sizes, as you can see here. So we normally use ASTM standard E8, which is applicable to it's a method to determine the tensile properties of metallic materials. So this standard tells us if it is a cylindrical sample, what should be the sizes of the grip, what should be the size of the gauge length, like a width or thickness. So it is a guide to test different metallic materials under a tensile load. So for today's exercise, as you can see here on this figure, we have a rectangular sample. The thickness of this sample is 1 millimeter, and the width of this sample, of the gauge length. This is the gauge area, okay, on which we actually attach a contact extensometer. So the width of this sample is 6 mil, as you can see here. Okay, so how do we start the test? This is a strain gauge. We call it contact extensometer. Okay, so we attach this on the gauge length, and once the machine will start applying the tensile load, this will open up, and this strain gauge is calibrated, and it will actually measure the strain. It records the strain in the gauge length. What is strain? It is the change in length minus original length. Okay, so this will actually give us the values of the strain. So once we have applied a sufficient load, at some stage this metallic material will fail under a tensile load. It will fracture. It will be a permanent fracture. So after the tensile testing, what we actually obtain, as you can see here, this is a raw data file. So we obtain values of the displacement, how much these two gauges, they actually these two grips actually displaced from their initial point. Then we have force, how much force this machine has applied on the material, and these values of the strains, which are in millimeter per millimeter, it is actually coming from the extensometer, which is a strain gauge. So normally we obtain these three data, like it is a data which we actually obtain after tensile testing of any metallic biomaterial. Now we can calculate or evaluate number of properties from this data set. For example, elastic modulus. We can obtain yield strength of the material, and we can obtain ultimate tensile strength, and we can obtain percentage elongation of the material or the strain of the material. Okay, so these are four important mechanical properties that we can actually evaluate from this raw data. So today I will show you how to do it. There's a very easy way to calculate all of these values. So we will go one by one. So okay, I will just put it here to create some space. So the very first step is to calculate the cross-sectional area of this tensile sample. I'll bring it back. So for this sample, as we are testing the gauge length, this gauge area of the tensile sample, and we know that the cross section area of a rectangle is like its thickness multiplied by width. So we will apply this formula here. I will just write area, and here I will apply a formula like it is width multiplied by thickness. So I will divide this with by 1000, because we will obtain everything in SI units. So, and this will be multiplied with thickness, and thickness we will also divide by 1000. All right, so we have this area, and the unit for this area is square meter. So we just write it so that we don't forget. And yeah, there you go. So this area, this is the cross-sectional area of this tensile sample that we have actually tested in under this machine under tensile loads. All right, so I will just highlight this one. All right. So the very first step is to calculate the area. Number two, we will actually calculate the stresses in this material. So I just write stress. It will be in the unit of pascals. And yeah. All right. So we know that stress is force per unit area, right? So we have to apply a formula. As you can see here, the values for the force is changing. When we started the test, it was 0, then it went to 25 Newton, 56, and so on, until the sample fails. It fractures. Okay, as you can see here, it's increasing up to 3000, 3400 and something. Anyway, we go back and we apply this formula. So here I put in this cell is equal to force. I select this cell divided by area. So this is the area of the tensile sample, and this cross-sectional area will stay constant. Okay, so if in Excel, if you want to make any value constant, so we have to apply a dollar sign before the alphabet and before the digit. So the cell number was L6 for the cross-sectional area. In order to log that, we apply a dollar sign, and I go enter, and this is the value of the stress. Now, if I want to apply this formula on the whole column, I will just come at the right corner. When you see this plus sign, double click that, and this will apply a formula on all uh, of the whole column. Okay, so if I go from here, shift control down key, this is the last cell. So you can see here we have this formula applied. If I click the second cell, you can see that it is changing the cell number, the second value of the force, which is 25.74 B4, but it is not changing the cross-sectional area because we locked that. So this is how you actually calculate stress. Okay, so yeah, now we will actually plot force versus displacement curve. Okay, we go select these two columns, insert, and here we will actually plot this curve. As you can see here, this is force versus displacement graph. Okay, and I just double click, start from 0. So all right, I will do some formatting. In here I will add primary axis like displacement in millimeters, and then I have my vertical axis. Oh, sorry. Chart axis title, vertical axis, it is force in Newton. Enter. So this is my force versus displacement curve for this tensile sample. All right. So now when we are trying to calculate the first mechanical property, which is elastic modulus, we know that elastic modulus, it is actually corresponds to the linear portion of the curve, right? Okay, just a moment. I need to have these. Okay, I will do it again because I need these numbers. So chart title, vertical force in Newton. Yeah, no, it's okay. All right, so we can see here from 0 up to maybe 1500, we are sure that this is a straight line. Okay, so we have to follow this. So maybe from 0 to 2000 Newton, it is a straight line. So we can mark this like from here. It okay from cell number 3. I'll change the color. Okay, from maybe, yeah, I'll do like this. From cell number 3 to maybe I go up to 2000 Newton. So I need to find 2000 Newton in the force column. So here is 2000. Okay, so I will just highlight this, and this is cell number 81. Yeah, 81. All right, so from cell number 3 to cell number 81, it is a linear portion of the curve. Okay, we will just highlight this from our force versus displacement curve. Okay, I just bring it here. All right, now I will plot my stress versus strain curve. Okay, so I just select the stress column, plot it. There we go. And in here, I will right click on the graph, select data and edit. And in the x-axis value, I will just enter the value of the strain. So it is 12,353. So I will put the same number here, 12,353, to plot this curve. So if it doesn't work, just go back and make sure that you have the right number here, 12,353. Press OK. All right, and there you have a stress strain curve. I just start from 0, so I just change the axis. There you go. So it is stress versus strain curve for this tensile specimen. There you go. So in here, now I will add the titles. Primary is strain. In millimeter by millimeter. And for chart design, axis title, in vertical, I have stress. Okay, one thing we can do, yes, you can see these numbers. If you double click on this vertical axis, then in the display units, I can change the units to millions, 10 raised to the power 6. So this will make this to display a little bit easier, because if these are the stresses, then we can write it. Now this is in megapascal, 10 raised to the power 6 instead of Pascal. Okay, so there we go. And I just make it bold so that it can be easily viewed. So this is the stress strain curve that we can actually plot from our stress and strain columns. All right, if I click here, you can see that this is stress and strain for this curve. Okay, now I have to plot the linear portion of this curve, and the slope of the linear portion actually corresponds to the elastic modulus of the material. So we know that the linear portion of this curve from our force versus displacement curve, it is from cell number 3 to cell number 81. So what I will do, right click on this graph, select data, and in here, or I can do one more thing, which is much easier. I will just make it smaller and copy this graph, whole graph. Just click anywhere on the graph, copy, and paste it somewhere else. So now I have two graphs. So I can play with one. Like for the first one, I will change the data set. Like I will make it up to cell 81. And in here for the D values, which are the stresses, I will make it 81. All right. Now I can see that this is the straight line from the stress versus strain curve. Okay. Now if I click on this line, if I go to chart design, add elements, I can make a trend line. We do a curve fitting. Okay. So in trend line, I will go linear because this is a linear portion of the curve. I will click here linear, and I will go to more trend line options. Here I will select linear, and in here I will say display equation on chart and r squared value on chart. There we go. Now we have this equation. I just bring it here. I will just make it a little bit bigger so that it is easily viewed. I will just make maybe 12. Yeah, and I double click on that on this box. Go to category number. I select a number, and there you go. Now the equation of the straight line, it is y is equal to mx plus c. C is the y-intercept. M is the slope of this equation. In this case, it corresponds to elastic modulus of the material. So the very first mechanical property, it comes from the curve fitting. So now we have this value, so I will just write it here. Okay, make some space, so I just write it here. 40.917. If I just do a renumbering, then I can see that this is 10 raised to power 9. So it can be in gigapascals. There you go. There you go. It was 40.917.264.533.83. So I just rounded it off, and it is 40.917 into 10 raised to power 9. So it is gigapascal. So in this way, we actually calculate the elastic modulus of the material from our tensile stress strain data. Now the second property which I have to calculate, it is the yield strength of the material. So yield point, it can be anywhere. If you look at the linear portion of the curve, as the load increases, then we have the material going in a plastic deformation. Okay, so we can see that we have to find this point. So normally, what we do, we actually do an offset. So the linear portion of the curve is offsetted by 0.2%, and the intersection point on this curve, it actually corresponds to the yield point of the material. So how do we do that? So I will show you how to do it. So I will just write 0.2% offset in strain. Okay, so I will check a strain, the first cell for the strain, which is C3, plus 0.2%, which is 0.002. So enter, and I have this value. I go to this box, go to the lower right end, and when you see this plus sign, double click, and now this formula is applied to the whole column. Okay, C4, C5, C6, and etc. So shift control down key, and I just do like this. All right, now we have 0.2% offset. Okay, that we can do it here. Now we need another value. This will be the x-axis on this same graph. Now we need another column. It will be 0.2% stress. Offset. And here I will write stress. There we go. All right. So now we know that I will just write it here just to show. E is equal to stress by strain. Okay, so this is the Hooke's law. All right. So according to this formula, if I multiply strain with the elastic modulus of the material, which is E, then it will give me a value for the stress, right? So this is the Hooke's law. So I will apply this one here, the value of strain, which is here. For the 0.2% offset, I will just need these strain values, the original strain values, multiply by the elastic modulus of the material. Oh, sorry, just a moment. So we need this value here. So strain multiply by the elastic modulus of the material And this elastic modulus, we need to make it constant. So I will apply dollar sign before alphabet and after alphabet. So there you go. And then I will multiply by this 1E9, which is gigapascal. So enter and I will get this value. So after this, we have to apply it to the whole column. So I will just come to the lower right and double click. And after that, control shift down key just to make these borders. And now we have uh, this 0.2% offset stress, which we can actually plot with this stress strain curve. All right. So now we have to plot them together to see the intersection point. So how do we do that? So if I right click on this graph, select data, I will add another series. I will call it 0.2% yield strength. For the x-axis value, these will be the 0.2% offset strain. So maybe I will just click the first and shift control down key. There we go. And similarly, for the y-axis, y values, I delete everything, go back, uh, check the first cell, shift control down key, and there we go. And press OK. All right. And if I go back, I can see that, oh, this is not plotted. Okay, let me check 0.2%. Oh, that's why. So we have to write 750 here. In Excel, sometimes it happens. Okay, so right, it should be okay. I will do it again. Okay. Okay. In x-axis, I will just check these strain values. Okay, up to here, which is up to 750, and I press OK and OK. I go back, and there we go. We now have this straight line, and it is actually intersecting this original stress strain curve, as you can see here, right? So if I double click on the vertical axis, I make it 1E9, enter. So I just change the axis to have a better view. Or yeah, now if I zoom in, if I go to view, zoom up to maybe 400. So if I scroll down, I can see the intersection point. So if I move my mouse cursor here, so you can see that I have a coordinates x and y. In the y coordinate, I have this value which is 44987296.3. I need to note it down. So I will just go back. Yeah, it's 449.87. Okay, if I round off, divide with the million, like 10 to the power 6, then I will obtain this value in megapascal. Okay, so it is 449.87 megapascal, which corresponds to the yield strength of the material. Okay, I will just round off 449 megapascal. There you go. So this is the second value that we can actually obtain from the stress strain curve. I can round off the elastic modulus as well, so I can just simply write it 41 gigapascal. Or just leave as it is, yeah, because we use this value for the calculation of yield strength. Okay, now for the ultimate tensile strength, if I go back to this graph, then I can see that this is the highest value of the stress in the stress column, in the original stress versus strain, like this one, the first column for the stress. Okay, and this value will actually give us the value of the ultimate tensile strength. So how we can calculate that? It is simple. I will apply this maximum formula. Okay, so maximum of column D, which is the, and from memory it was up to cell number 750, but double checking, you have to select the whole column. So the maximum of this column is this one, and I will divide this by 1 million, which is 10 to the power 6. And now this value, it is in megapascal. Let me just write this one down. All right. Similarly, so you can see that after the permanent fracture, we have this value of strain. So this is the maximum strain in the material. It corresponds to the x, which is 0.120. So I can simply apply a formula. Maximum on the strain, the strains which were recorded by the extensometer, and I will just write it 750. Okay, so column number C3 to 750, C750, the maximum formula, up enter. And now in order to calculate this, because the units of the strain were in millimeter by millimeter, if you want to obtain this value in percentage, I will simply multiply this with 100, and now I have this value here, right? So now I have obtained the four important mechanical properties from this stress strain tunnel. Like we have elastic modulus, which is 40.917 gigapascal. The yield strength of the material, it is 449 megapascal. And UTS, which is ultimate tensile strength, it is 591.90 megapascal. And the elongation in this material, it is 12.09%. So in this way, we can actually evaluate the mechanical properties from a given raw data which we obtained after the tensile testing of a metallic material. I hope this will help you to analyze the raw data that you have after the tensile test, and you will find this video helpful. Thank you.